Hello everyone. In the previous video we have seen linear differential equation and different types of linear differential equation, that is basically depending on the value of phi x, that is homogeneous differential equation and non-homogeneous differential equation. Today in this video we'll see the solution of homogeneous differential equation, method of finding solution for homogeneous differential equation. So the standard differential equation in terms of differential operator can be written as dn y plus dn minus 1 y, and we have a constant, that is a1, plus a2 dn minus 2 y plus, and so on, an minus 1 dy plus an y is equal to phi of x. This is the standard form of linear differential equation using differential operator, where d is a differential operator. Now depending on the value of phi x, so if phi x is equal to 0, then we call it as homogeneous differential equation. If phi x is not equal to 0, then we call it as non-homogeneous differential equation. So today in this video, let's see how the method of finding solution for homogeneous differential equation. To explain the method of finding solution for a homogeneous differential equation, let me take a second order linear differential equation. The same method can be applied to or extended to equations of higher orders also. So let me write the second order linear differential equation. So d square y by dx square plus a1 dy by dx plus a2y is equal to 0. Now in terms of differential operator, the same differential equation can be written as d square y plus a1 dy plus a2y is equal to 0. Now I'll simplify this. So we have d square plus a1d plus a2 into y is equal to 0, where this same equation can also be written as f of dy is equal to 0, where f of d can be taken as d square plus a1d plus a2. Now since it is the second order differential equation, we have a equation which looks like a quadratic equation. So obviously it will have two solutions. So let me take two solutions, as one as y1 and the second one is y2 are the solutions. And it is also true that c1y1 plus c2y2 will also be the solution for this. Where c1 and c2 are constants or arbitrary constants. Now let us verify this, whether this is a solution or not. Now if y1 and y2 are the solutions of linear differential equation, then we can write, or it has to satisfy, f of d y1 is equal to 0 and f of d y2 is equal to 0. I have written this because we have taken y1 as a solution, y2 is also solution. When these are solution, it should satisfy the equation. So we can write f of d y1 is equal to 0 and f of d y2 is also is equal to 0. Now let me verify this. So if I take f of d c1 y1 plus c2 y2, then the same thing can be written as c1 f of d y1 plus c2 f of d y2. Now from these two I can write c1, this is 0 into 0 plus c2 into 0. So this also gives us 0. So we can say that y1 is a solution, y2 is also solution, and this, that is c1 y1 plus c2 y2 is also solution, is also solution. Now in order to find the solution of the given linear differential equation, there is some method. So basically we have to write the given linear differential equation in the auxiliary form. So let's see how to do that. Now while finding the solution of the given linear differential equation, we take this solution, that is yc is equal to c1 y1 c2 y2 as complementary function. We call this as, or this is called as, all the three are solutions. Y1 is a solution, y2 is solution, and the combination of this, that is c1 y1 plus c2 y2 is also solution. But this is known as complementary function, complementary function, or simply written as CF. So we have seen previously, if a second order differential equation is taken, then fd can be written as d square plus fdy can be written as d square y plus dy a1 dy plus a2y, and this can also be written as, or from this, fd is equal to d square plus a1d plus a2. So this is something similar to quadratic equation we have. So if I replace d by m, then this becomes f of m is equal to m square plus a1m plus a2, and if I equate this to 0, that is for homogeneous equation, since this is 0. So we can find we can replace d by m. So f of m can be written as m square plus a1m plus a2. So now we can easily find the solution of this quadratic equation by comparing it to 0. So m square plus a1m plus a2 is equal to 0 gives us two solutions which can be taken as m1 and m2. Now depending on the values of m1 and m2, we can write different solutions for the given linear differential equation. So we'll see what are the different cases. So there are three different cases. So first one is real and distinct root, real and distinct roots. And second one what we have is real and same, real and similar, or real and coincident roots. And the third one is pair of complex roots, pair of complex roots. So these are the possibilities when we find roots of quadratic equation. So we'll see one by one these three different cases. So when we write f of d in this format, that is replacing d by m, the differential operator by some other character, that is m. So this gives me auxiliary equation, auxiliary equation. So you can treat this as AE. A is nothing but auxiliary equation. So in order to find the root, we have to take the auxiliary equation first, and auxiliary equation will be this, that is equal to 0. So then we find the roots, then we write the solution. So I say there are 3 cases. So first let us see the first one, that is case 1, real and distinct roots. Real and distinct roots. So if the auxiliary equation is this, m square plus a1m plus a2 is equal to 0. This is auxiliary equation, and since it is a quadratic, obviously we should have 2 roots, and if m1 and m2 are real and distinct roots, then complementary function yc can be written as c1 e to the power m1x plus c2 e to the power m2x. Let me take an example. So if you have solutions of a quadratic equation or a auxiliary equation, which can be given by this, as m1 is equal to 2 and m2 is equal to 3, then complementary function can be written as c1 e to the power 2x plus c2 e to the power 3x, where c1 and c2 are arbitrary constants. Now if suppose we have a third order differential equation, then the complement and the solution of that is real and distinct, solution of that is having a real and distinct roots, then the same method can be applied for that also. So we can write, if suppose the complement, the auxiliary equation is in this format, m3 m cube plus a1 m square plus a2m plus a3 is equal to 0. If this is the auxiliary equation, then we have m1, m2 and m3 are the 3 roots. Then complementary function yc can be written as c1 e to the power m1x plus c2 e to the power m2x plus c3 e to the power m3x. The same thing can be extended to n roots also. Now let us see the second case. Let us take the second case. Now if suppose the roots are real and same, if the auxiliary equation is of second order and it is having 2 roots which are real and same in value. So we can take m1 and m2 are the roots which are same. So we can write m1 is equal to m2 is equal to m. And then in this case yc will be equal to c1 plus c2 x into e to the power mx. Suppose the FM equation, that is auxiliary equation, is having roots 2 roots whose values are m1 is equal to m2 is equal to 5. Then yc can be written as c1 plus c2x into e to the power 5x. So this will be the complementary function. Now the auxiliary equation is of third order. Then obviously we'll have 3 roots whose values are m1 is equal to m2 is equal to m3, and I can equate it to m. All 3 are same. So we can write the complementary function for this case as c1 plus c2x plus c3x square to e to the power mx. Now the third case is, case 3 is if the roots are pair of complex numbers. Let me take the roots as a plus or minus ib. Then complementary function can be written as yc is equal to e to the power ax into c1 cos bx plus c2 sin bx. So this is a solution. For example, if the roots are 2 plus or minus 3i, then yc can be written as e to the power a. What is a here? 2. So 2x into c1 cos b is 3. So 3x plus c2 sin 3x. Let me take few examples here for different types of roots, how to write the complementary function. So this is the complementary function yc, and these are the roots. So the first one is if the roots are real and distinct. So this is a real and distinct root. So we know that c1 e to the power 3x plus c2 e to the power 2x. This is how we write. And the second one is we have real and distinct roots, but there are 4 roots. So we have to write c1 e to the power 2x plus c2 e to the power minus 2x plus c3 e to the power 4x plus c4 e to the power minus 4x. This is how we write for real and distinct. Now if suppose the solution is having a pair of complex numbers, then we have, since there is no real part here, so we can skip that e to the power ax term. So we can write c1 cos 3x plus c2 sin 3x. Now this is a pair of a complex number where there is a real and imaginary part. This is in this format, so I can write e to the power ax, that is 3x, into c1 cos 4x, that is bx, plus c2 sin 4x. Now if suppose it is having repeated roots, real and repeated roots, then we can write c1 plus c2x e to the power 3x. Now in this example, it is having 3 real and repeated roots and 1 root which is real but distinct root, that is it is not same as these roots. So you can write combine both the solutions of real and distinct and real and repeated. So this is for c1 e to the power 0x plus. Now we have 3 real and repeated roots, so we can write c2, since I have used c1 for this, I can write c2 plus c3x plus c4x square, and if there is one more minus 1, then you can add c5x cube and into e to the power this value, that is minus 1x. And this example, in this we have real and repeated roots and also pair of complex number. So we know that for real and repeated root we write like this, c1 plus c2x e to the power 2x, but it also has a pair of complex roots. So plus e to the power 2x into c3. Why I am using c3 here? Because c1 and c2 constants are already used here. So c3 cos x 1x, because this is b value here is 1x plus c4 sin x. And if suppose for example it is having pair of complex roots but repeated, say let me take 2 plus or minus 4i is repeated twice, so it is 2 plus or minus 4i. Then the solution will be e to the power 2x into, since it is repeated, I have to write c1 plus c2x cos 4x plus c3 plus c4x sin 4x. this is how we write the solution. So these are the simple examples which you can use in your solutions. So that's it. Thank you.